we've looked at indeterminate forms that you typically get when you do L'Hopital's rule of 0 over 0 or infinity over infinity. We're going to look at the other indeterminate forms and how you go and proceed about those problems. That's if you end up with like some multiplication of 0 and infinity, or subtraction of infinity, and then what you do if you get these exponential forms of 0 to the 0 power, infinity to the 0 power, 1 to the infinity power. All right, so the first one, we have the limit as x approaches 0 from the positive side of x times natural log of x. Well, if we were to put in 0 for this, we know that at 0, that's going to approach 0, so that's 0. If you put 0 in for this natural log, you can't do natural log of 0, but if we look at what the graph of natural log looks like, it looks like this. And so as we're coming in here from the positive side, this is going to negative infinity. So right now we have this indeterminate form of 0 times negative infinity. That means possibly we can use L'Hopital's rule, but you can't use L'Hopital's rule unless you are in one of those fractional forms that we had before. And so what you have to do if you get one of these forms is change it to a fraction. So what we're going to have to do here is move one of those two things down to the denominator. Try to find the one that's easiest to move. In this case, I don't think moving the natural log is very easy here, but moving x is not too hard. So let's keep natural log on top. On bottom, if we move x down to the bottom, now it's x to the negative 1, or that's also the same as 1 over x. So as we go to 0 from the positive side, our top now is still going to what we had before, negative infinity. The graph of 1 over x, if you look at that, looks like this. So as we're approaching 0 from the positive side here, that's going to positive infinity. That's one of those fractional indeterminate forms that we can use now to apply L'Hopital's rule. So now at this point, let's find our derivatives using L'Hopital's rule. Indicate that you're using it. Okay, so on top we got 1 over x. Our bottom derivative, probably be easier if we went back and thought of this as that x to the negative 1. So derivative there is just using our power rule. Now the new exponent's 1 less. Here now, I think we still have an indeterminate form, but don't apply L'Hopital's rule again. If they're all polynomials, simplify them. Let's move this back up and make it positive here. And so now our limit looks like this, 1 over x times negative x squared. Multiplying that together, we can cancel one of those x's. So now we have the limit x goes to 0 from the positive side of just negative x. And now if you plug in 0 to that, that's just going to be equal to 0. And so this one should be approaching 0 using L'Hopital's rule. So if you got multiplication, you got to move something down to the denominator to make it a fraction. Let's look at another case. On this one, compute the limit as x goes to pi over 2 from the left of secant minus tangent. Well, let's see what we get here. Remember, secant's the same as 1 over cosine of pi over 2. I believe if we do cosine pi over 2, we're not going to get we're going to get 0 here. So if we do cosine pi over 2, yeah, we get 0, and we can't have division by 0, which means this is probably approaching infinity or negative infinity. To check that, you could graph this one. So graph 1 over cosine x. And for this one, I'm going to use that trig graph number 7 on my calculator here. And pi over 2 would be that first line there, so you can see what's the graph doing here as we approach pi over 2 would be right here. Looks like it's going up into infinity. So this is giving us positive infinity minus, how about tangent of at pi over 2. You can try that one out too. You're also going to get something indeterminate here. Just showing you the graph of this one. If we graph tangent at pi over 2, same spot, we have an asymptote going up to infinity there as well. So this is infinity minus infinity. That's one of those indeterminate forms. So when you have fractions, or when you don't have a fraction again, you got to get into a fractional form. So what we're going to do here, rewrite it as a single fraction. Basically, combine these two things as a common denominator. And so what we're going to do is rewrite this limit and put it in terms of stuff we know secant and tangent are equal to, similar to what we just had up there a little bit before with secant. So this is 1 over cosine. Tangent's the same as sine over cosine. That's a common denominator now, so let's join these into one fraction of 1 minus sine over cosine. And now if we put pi over 2 in there, sine of pi over 2 is 1, so on top we got 1 minus 1, that's 0. Cosine pi over 2 is also 0, so that's one of those fractional indeterminate forms we can use to use L'Hopital. So now we'll apply L'Hopital's, take the derivative of both top and bottom. Derivative 1 is 0, derivative sine is cosine, so this is going to be negative cosine here. On bottom, derivative of cosine is negative sine. Now if we put pi over 2 in, we're going to end up with 0 on top. Sine of pi over 2 is 1, so we get negative 1 on bottom, but 0 divided by anything is going to give us a result of 0, and so this limit should approach 0. Okay, next one, limit as we go to 0. Sine of 0 here is 0, because if we plug in 0 here, 4 times 0 is 0, sine 0 is 0, so our inside becomes 1 plus 0, or just 1. Cotangent of 0 is going to be something we're going to want to look at here, so let's graph that out. Two ways you could graph that one. We don't have cotangent on here, so you could either do cosine over sine, or it's the same as 1 over tangent. I'm going to do that 1 over tangent here and graph it. So what's this one doing as we go to 0 here? From the right side, looks like as we come from the right side here, as we approach 0, this is going up to infinity. So this is giving us 1 to the infinity power. That is a indeterminate form where there's an exponent. So if you have an exponent of 0 to the 0, infinity to 0, or 1 to the infinity, we can do this, but what we're going to have to do is rewrite the equation by taking the natural log of both sides, then convert it into one of those fractional forms. All right, so let's go back to this one. What we're going to do is we're going to set y equal to this limit. And then we're going to natural log both sides. So we're going to take natural log of this side, and we're also going to natural log the other side here. And by natural logging it, what that allows us to do is remove the exponent and bring it down using our log property. So we can take this, move it down here. So now our limit is going to be cotangent of natural log of 1 plus sine 4x. All right, so at this point now, what we still have is we know that this cotangent as we go to 0, that's infinity. If we put 0 in for the sine part again here, 4 times 0, 0, sine of 0, 0. 1 plus 0 is 1, so we'll end up with natural log of 1, but natural log of 1 is 0. So we still have indeterminate. Now it's in that multiplication form that we saw in a previous problem, but we still can't use L'Hopital's like that. So when it's multiplication, we got to change it into a fraction. So which of these two functions, cotangent or natural logs, most easily put to the bottom? The cotangent is, because the reciprocal of cotangent would just be tangent. So I'm going to leave the natural log part alone here. Cotangent, moving it down to the denominator would make it the reciprocal, so tangent. Now let's check our indeterminate, see if we get indeterminate form. Top here is still going to be 0. Tangent of 0 is 0. So now we have an indeterminate form we can use L'Hopital's with. So now what we're going to do, apply L'Hopital's rule here to our limit. So on the right side, we're going to take derivative. Derivative on the bottom is secant squared. On top, we're going to need to do chain rule there. So the derivative would be 1 over all that stuff we're taking the derivative of. But we got to do chain rule. So now times the derivative of the inside. Derivative 1 is 0. It's a constant. Derivative sine is cosine, but it's kind of like chain rule again. Leave that inside alone, but now derivative of this very inside, derivative of 4x is 4. So that would be our derivative. Now let's see what we end up getting here. I'm going to figure this out, I'm going to move this secant squared back up. The reciprocal of secant is cosine. So that's going to give us, we got that 4, we got the cosine 4x here. If I move that secant squared up, that's going to be cosine squared over 1 plus sine 4x. So what would we get if we plug in 0 now? Well, sine of 0 is 0 for the bottom, plus 1 would be 1. So we're just going to get 1 on the bottom. On top, cosine of 0 is 1, so we'd have 4 times 1 times 1, which would just be 4. So now it looks like we got natural log equal to 4 over 1, which is just 4. We're not finished though. We need to know what y equals, not what natural log of y equals. So the last step is to change this, and we can change it by changing from log form to exponent form. Remember, our little base on natural log is log base e. So if we change this to exponential form, it would be e to the 4th power. This limit is going to approach e to the 4th power. So when you're doing these exponential ones, once you are done doing L'Hopital's rule here, you got to remember that you use natural logs at the beginning, so your final answer is going to be e to whatever that answer you got for your limit is going to be. Why don't you try the video, pause it, see if you can do this one. This is very similar, where you're going to have an exponent to an exponent right now, because this would be 0 to the 0 power. That's an indeterminate form. See if you can apply some of the stuff we just did and find this one. All right, let's see how you did. Since we can't do this limit here, 0 to the 0, set y equal to this. And then take the natural log of both sides. Okay, what that lets us do now is bring that exponent down. So we got x times natural log of x. That's an indeterminate form right now of 0 times negative infinity. We need it in fractional form, though. We've seen this one already before. If we move that x down, this is going to become natural log x over x. That's an indeterminate form now of negative infinity. X to the negative 1 if we bring it down. which should give us positive infinity. That's an indeterminate form. This is that exact same problem we looked at earlier. So I'm not going to go back through it, but you can see that the result ends up being 0 here. So if you follow this through, we're going to end up, after using L'Hopital's, getting this equal to 0. Last step, you got to change it to exponential form, so you get e to the 0 power or 1. So the answer to this one, if you got it correct, should be 0. For the work here, again, see the previous problem for that work if you did not get that to come up.